loss mechanisms, we can divide them primarily into 3 categories in practice. So one is optical losses. So optical losses are essentially accounted for by the external and internal quantum efficiency and primarily impact the short circuit current density. So basically the optical reflection losses and also any, for instance, infrared in the case of silicon or red photons that might be lost by poor back surface reflector. So those are all in the optical loss category. The other very important category is recombination losses, both surface and bulk recombination losses. And these are accounted for by the internal quantum efficiency. And actually, they impact all of the key parameters, JSC, VOC, and field factor. And the third category is resistive losses, which are essentially electrical ohmic losses. And these are primarily accounted for by the field factor. And indirectly, they also affect the other parameters. So for very high efficiency cell design, you have to minimize all of these losses. Now, actually, Dick Swanson, founder of SunPower, has done a very informative analysis of the loss waterfall as you go from thermodynamic limit towards the practical commercial cells. And basically, based on Dick Swanson's waterfall chart, you see that the theoretical limit for single junction crystalline silicon is around 29%. That's because in practice you have to account for band-to-band Auger recombination and also the finite mobility of the carriers. And at the time of his publication, the best commercial cell, which happened to be SunPower cell, was on the scale of 21.5%. And actually, since then, this has risen to now the best commercial cell at 24.1%. And this is also a SunPower cell. So you might ask, what is the, in practice, how high we can make the efficiency? You know, based on what I have seen, I would put that maybe possibly in the range of 26 to 27% practical limit for crystalline silicon. So there is single junction crystalline silicon. So there is still a lot of room for improvement of efficiency. So if you look at a practical solar cell, this is how you can represent that in terms of lump model, a current source in parallel with the diode, which has your dark current, and a shunt resistance and a series resistance. The ideal solar cell, actually, this shunt resistance would be infinite and series resistance would be 0. Now, if you take an ideal solar cell with those conditions, then field factor directly, this is a practical formula, empirical formula that depends on VOC. So the higher the VOC, the higher the theoretical field factor or pseudo field factor. Now, in practice, of course, you have a finite series resistance and you have a finite shunt resistance. A lot goes into managing these in the cell design and processing. If you take an ideal cell, for instance, this is your maximum power point, and as the series resistance increases, you essentially move away from or degrade the squareness. The maximum power point drops, maximum power drops. The same thing with shunt resistance. Also, shunt has another disadvantage that the smaller shunt resistance can also degrade your low light performance, which is bad for energy yield of your panels in the field. So basically, in practice, we need to minimize series resistance and maximize shunt resistance. So let me give you a brief overview of the mainstream crystalline silicon solar cells and modules. If you look at most of the cells and modules in the industry that are made today are front contact, front junction, or front emitter junction cells. They're actually this is a typical front contact front junction, mostly made on 156 millimeter format wafers. Whenever you see the pseudo-square format, that means it's typically it's a monocrystalline wafer, the starting wafer, and when it's a square cell, usually it's a multicrystalline cell that comes from cast bricks. The front side is silver, so of course it also causes shading losses. After silicon, it's in terms of material cost, it's the second cost in your cell. There are majority of the cells are made using P-type silicon, and there is also a lot of interest in what's called cast mono or quasi-mono, which is really an improvement of the cast multicrystalline with a seeding arrangement that you essentially create near monocrystalline CZ performance, but at a cost that is much closer to a multicrystalline cost. So if you look at, again, the mainstream cells in the commercial cells, pretty much every one of them goes through, starting with the wafer, then it goes through somewhere in the range of 6 to 8 process steps. So you start with the wafer, you have to remove the saw damage, and then texture it, and then form the emitter, which is a front junction phosphorus emitter. Typically, this is done with a puckle or phosphorus diffusion. Then you have to isolate the edge to make sure that you don't have puckle wrapping around, and then put the front side passivation, which is typically silicon nitride passivation. It also serves as anti-reflection coating. And then you screen print silver on the front side, the pattern, sort of the edge pattern, and then aluminum paste on the back side, and then it goes through the fire-through metallization at the end, and the cell is ready. So that's the typical process. If the higher efficiency front contact cells use what's called selective emitter. So that means your emitter, which majority of your emitter is lightly doped or high sheet resistance, so that you don't degrade the blue response of the cell in the higher photon energy range. And then where you make the contacts with silver, it's heavily doped for low contact resistance. So cell efficiencies 15 to 19%, depending on mono versus multi and selective emitter, or no selective emitter, homogeneous emitter. And then this translates to module efficiencies that are on the low end around 13%, on the high end 17% for mainstream technologies. So this here actually you see the efficiency trend. This is basically for thin film and also crystalline silicon, which is multi and mono. And of course, you can see that there is a gap. There is when you look at the thin film technology, it's trailing crystalline silicon by around at least 3% in efficiency. And again, this trend, they both are going to go up in efficiency, but the gap will continue. And again, there are exceptions to the mainstream, right? So of course, some power panels, high-end panels today are over 20% efficiency. So that's almost 8% efficiency advantage over thin film. As of next year, they're going to ship their latest technology, Maxion, over 21%. As we establish scale, we go to market at 20%, and then we forecast 22% in the next 4 years. Now, the mainstream crystalline silicon technology, actually, there are significant transitions and trends happening to enable higher and higher cell and module efficiencies. Here I'm focusing on the cell. What are the key trends in cell? For instance, transition from homogeneous emitter to selective emitter, as I described earlier. The other part is that in most of the cells made today, the back side has a blanket so-called aluminum back surface field. That in higher efficiency cells is being replaced with dielectric passivation with local contacts. Sometimes you hear the terminology PERC, which is really passivated emitter, and rear contact, localized contact. And then also a lot of interest in so-called field-assisted passivation. Not only you improve the interface, but also you rely on fixed charges, depending on the polarity, to improve the efficiency. We utilize that very effectively in our thin silicon technology. And again, another important trend is really the front contact transition to back contact, because when you take the contact or metallization to the back, essentially you eliminate, particularly in the case of interdigitated back contact, you completely eliminate the shading losses that are due to the electrode on the front side. There are some companies that are making or are making transition to the heterojunction emitter cell on crystalline silicon. A good example here is Panasonic Sanyo that has been doing it for many years. And then, as I mentioned, silver cost is a significant cost factor, component of cost in crystalline silicon mainstream. There is also a lot of interest in replacing screen-printed silver with copper plating to reduce the cost. And then also Czechoslovakian silicon to seeded cast mono, so that you can get near mono efficiency performance at a lower starting wafer cost. So actually here I have summarized essentially the PV performance landscape. If you look at the thin film technologies today and the projections over the next couple of years, it's really up to 13 or 14%. This is actually where crystalline silicon starts. The efficiency of low-end crystalline silicon modules starts. This is a mainstream crystalline silicon. As I described earlier, module efficiencies in the range of 13 to 17% efficiency. And in this case, the higher efficiencies more and more rely on selective emitter. And again, leading technologies with dielectric passivation. There is also significant interest to replace P-type silicon with N-type silicon. And that actually can give you a significant performance advantage. And really, there is general agreement that if you want to get the cell efficiency over 20%, you really want to go to N-type silicon, higher lifetimes. And also, you eliminate the what's called light-induced degradation, because you don't have the mechanism of boron-oxygen pairing defect in the N-type silicon. So a very maybe brief discussion on motivation behind thin silicon, thin crystalline silicon for high-efficiency solar cells, because we operate in the thin silicon regime, much thinner than the typical 180 micron wafer. So really, one very important reason is that the VOC limit, theoretical limit for crystalline silicon, actually increases as you reduce the thickness of silicon. And the really VOC limit is theoretical limit is governed by the Auger recombination, and the limit of Auger recombination increases with thinner silicon. In the case of Solexel, we operate about 40 micron absorber, so that gives us a theoretical limit of 790 millivolts. It's actually much higher than if you, let's say, you take a 200 micron typical cell theoretical limit. So if you look at this graph, for instance, VOC limit increases by 50 millivolts when you reduce your silicon thickness from 300 micron to 20 micron. So this is a very important driving force for using thinner silicon. Now, really, another way to look at this is that for a given material quality in terms of effective lifetime or effective minority carrier diffusion length, thinner silicon actually gives you a higher multiple in terms of L effective over silicon thickness. That higher multiple is very important to achieve both high VOC and high JSC. Just very quickly, in the case of silicon, actually bulk lifetime, we have dealt with lifetime improvements and design rules related to lifetime for since the start of the company. So it's very important to achieve high effective lifetime for high efficiency cells. Silicon lifetime is actually dominated by the defects and Auger recombination. Now, primarily in the case of lighter doped base, it's defects, and then when you have very high quality material, and as your doping gets above 1E17, then you're limited by Auger recombination. So now, effective lifetime actually depends on bulk lifetime, surface recombination, or what's called surface recombination velocity, and absorber thickness. And when you have, now one of the important things to remember is that as you go to thinner absorber, thinner silicon, it puts special demand on very high quality passivation. So you have to have extremely good surface passivation, because now you could be dominated by the surface recombination and not bulk recombination. So if you make your surface passivation very high quality, in our case we do that with proprietary passivation both on the front side and back side, and relying on field assisted passivation as well, then your effective lifetime really is governed by this expression. So basically, for very high quality surface, ideally, if this SRV, surface recombination velocity, is 0, then essentially your effective lifetime is your bulk lifetime. So obviously, we don't want to be here, because your lifetime would be very low. In the case of Solexel's cell architecture, basically, we have a design rule that, I'll just summarize it, but we have a design rule that demands that L effective, or effective minority carrier diffusion length, should be at least 15 times thickness of the absorber. This is particularly a requirement for high VOC, and it meets JSC requirement. JSC requirement is lower, actually, a lower multiple. And basically, for 40 micron silicon, this translates to 300 microsecond lifetime. We like our surface recombination velocity to be less than 5 centimeters per second. These are for very high efficiency cells in the range of 23% plus efficiency. We are actually fairly close to these numbers with our champion and mean efficiency cells now. You can see that again, for a given material quality, you would much rather be thinner as long as you have a very good surface passivation. Now, if my silicon thickness is 4 times or 40 micron, go to the wafer range, then my lifetime has to be at least 16 times better. So instead of 300 microsecond lifetime, I would require maybe 5 millisecond lifetime. So you see that, and that would be a very expensive wafer. So that's why thin silicon allows us to achieve very high efficiency, but with more practical material quality that we can achieve. So why thin, again, taking it to why thin epi silicon, right? So very quickly, with epi, actually, we reduce silicon consumption. That's part of our cost reduction. We do achieve high quality material in terms of minority carrier lifetime, over 300 microseconds. We can do in situ doping, so we can modulation dope our absorber as we grow. You cannot do that in the case of wafer, of course. We can achieve higher open circuit voltage. We already do that routinely compared to the standard cells. And also thin silicon has excellent synergy with interdigitated back contact architecture. You like to have thinner silicon with the back contact, back junction architecture. Lower temperature coefficient because of a higher VOC is another very important benefit. Cooler normal operating cell temperature. We have actually shown that. And overall enhanced yield because of all of this. And thin silicon, if you slightly bend this or drop it, it will shatter the standard cell. But in the case of Solexel, we can make semi-flexible cells that can be conformal to curved surfaces, and we can package them without glass. Very lightweight, much lighter weight than glass. So now there have been significant challenges to adopt thin silicon for solar cells. And what we have done at Solexel over the last, since founding the company, we have come up with very practical solutions based on our approach. Our solutions are based on epitaxial silicon liftoff and all the manufacturing technology that goes with that. Template and backplane support. We never handle or process thin silicon standalone. There are a couple of unique tools in our flow that we have developed with key manufacturing partners for very high productivity. And again, I mentioned the field-assisted passivation.